Hello everyone, this is Team 9 from iGen 230. In this video, we will talk about our final product, PowerUp, which is a power system that can motorize manual wheelchairs. In this video, we will first introduce the background of our project. Then, we will present our product in details. At the end, we will talk about the outcomes that are achieved in this project and some future works that can be done if it is to be continued by another team. Today, wheelchairs can be broadly classified as either powered or manual. The manual wheelchairs are more likely to be introduced first to people who are mobility disabled, as they are more affordable than the power wheelchairs. However, for people with progressing mobility needs, their needs for the functionality of the wheelchair can change over time. This leaves them with two options. They can either switch to powered wheelchairs or install power boosters on their original manual wheelchairs. However, both options can be prohibitively expensive. As not every wheelchair users can afford switching to power wheelchairs or installing expensive power boosters, our product, PowerUp, will strive to fill this gap. PowerUp is a power system that allows wheelchair users to upgrade their manual wheelchairs at a low cost. The system will be versatile and easy to use by the users themselves. After learning about the stakeholders' needs by interviewing an older wheelchair user and a younger part-time wheelchair user, our team has determined the following requirements. The weight of the system should be less than 15 kilograms, and the system can be installed when needed and uninstalled when it is unused, with the installation time being within 30 minutes. It should also be easy to operate by the users themselves, and it is rechargeable. The design must accommodate the weight of at least 90% of the users.
This is the CAD model of the wheelchair with PowerUp implemented. Note that this model does not include the wirings. First, we have the joystick mount on the right side of the wheelchair near the armrest to control the direction and speed of the wheelchair. Then, we have the friction drive system on both sides to drive the wheelchair. They are attached on the armrest by the orange adjustable tension straps. The system will be controlled by the Arduino board and H-bridge, which are placed in the box below the wheelchair. The power of the system is driven by the 12-volt output battery, which is placed in the middle of the crossbar below the wheelchair.
Now moving on to the electrical components for this project, we decided on a simple yet effective circuit, something that was lightweight, easy to use, easy to install, and cost effective. The circuit you can see in front of you consists of just a joystick, an Arduino, a dual motor controller, two DC motors, and a 12-volt battery. Before moving forwards though, we needed to determine some simple power calculations to figure out how much power you need to move a 180-pound person at 5 kilometers an hour. To do this, we used a simple calculation to find F net. We did this through finding the force of gravity, the force of friction, and the force from drag. Once we found this, we summed them and timed it by the velocity, and we got the power. Once we determined the required power, we moved on to choosing parts. First, we chose the joystick as it was a simple and easy to use user input. It allowed for finite control of both motors and was simple for any user. This also allowed for finite movement in the X and Y direction for speed and turning radius, so we can move slow, fast, turn sharp, or turn slowly. To collect user inputs from the joystick and act as the main control board for the electrical system, we landed on our Arduino Uno. This will convert inputs from the joystick into PWM control, which could then tell the motors what to do. And it also offers some good expandability for possible future work. If we wanted to include a speedo or battery management systems, we could use this Arduino to do that, and it would offer some good expandability. Now, once we've converted user input to PWM controls using the Arduino, we can pass it on to the motor controller. We decided on a dual motor controller, very similar to the line following robot, although this one can handle an input of 24 volts, but also output 24 volts each. It also has a 7 amp max peak draw, although the motors even at stall currents that we're using won't even draw 7 amps at the peak. This motor controller, combined with the Arduino and joystick, allows for really finite control of the motors themselves and allows for the user to move the wheelchair slowly forwards, backwards, left and right. Now, what we'll be powering with this H-bridge are two high torque electric motors. So these are 12-volt DC motors with a peak current draw of 2 amps in full load. The stall current draw is 6 amps. So they approximately output 3.4 kilograms per centimeter of torque. But what's more important is they output about 21 watts of power each, or 42 watts total together. We're going to have them mounted on each wheel, and they rotate about 200 RPMs. At 42 watts total and 200 RPM shaft rotation, This should be enough to drive the wheelchair with a 180-pound person at 5 kilometers an hour, no problem, especially when the friction drive is connected to the much larger drive wheel of the wheelchair. Now finally, powering these motors is a 12-volt, 50 amp hour lead-acid battery. We landed on the tried and true lead-acid batteries. We wanted something that was affordable and reliable. Although weight is a concern here, the lithium-ion batteries are a lot more expensive and have their own issues. Determining the size of this battery was the next difficulty we had. We calculated the worst case scenario where the wheelchair was running at full speed, up the maximum grade of 8%, while having a 180-pound person on it, and we wanted to determine how much power or amperage we needed to travel a total distance of 5 kilometers. What we landed on was a 15 amp hour battery, was more than enough to do this. This covers all of the electrical components in the electrical circuit. Although it's simple, we hope for it to be effective and reliable and be able to be used for a long period of time.
Moving on to the mechanical elements of the system, we begin with joystick mount, which is designed for users with reduced mobility and can be mounted on any standard wheelchair arm. The battery mount can support up to 6.5 kilos and is securely mounted to the lower crossbar of the chair with carbon fiber clamps, keeping the center of gravity low for improved safety. The control module contains the Arduino and the H-bridge and is printed in ABS. It is designed to be mounted with flexible straps so that the user can determine the optimal placement for their particular chair. The motor mount and housing are mounted to the arm of the wheelchair using the same flexible straps as before. The inner mount moves within the outer channel to provide two locking positions: driving, where the drive wheel contacts a tire, and free, so that the chair can be pushed manually with the system installed. The locating bolts and nylon spacers that connect the inner and outer modules allow small adjustments to the height of the drive wheel to improve contact on chairs with varying dimensions. The friction drive wheel transfers power to the wheelchair by pressing on the chair's tire. The wheel itself has a high coefficient of friction to reduce slippage, as well as grooves in the contact surface to reduce water buildup. A custom machined interior allows it to be mounted directly to the motor shaft. This choice of drive system is economical to build and requires absolutely no modification to the wheelchair frame, making it ideal for this application.
Similar to how the line-following robot moved, altering the speeds of the left and right motors controls the direction of the wheelchair. The main loop in the code takes two instantaneous analog readings ranging from 0 to 1023, which corresponds to the X and Y position of the joystick, and then converts them to a PWM value between 0 to 255 using the Arduino map function. The PWM values are then sent to each motor via analog write. Here are examples of the general direction conditions for the joystick. At the center position of 511 and 511, both motors are set to 0 and the wheelchair is at rest. Moving the joystick up on the y-axis to 511 and 1023, both motors are set to 255 PWM with the wheel spinning forward. Moving down to 511 and 0, again these are both set to 255 PWM, but the reverse function is called, and the wheels are spinning backwards. At 0 and 511, the left motor is set to 0, and the right motor is set to 255 to create a left turn. Similarly, at 1023 and 511, the opposite is in effect to make a right turn. We tested the motors and electrical subsystem by building the physical circuit and powering it by a constant voltage source. The following clip demonstrates that the motor driver and joystick perform as expected to control the speed and direction of the motors when connected to a 12-volt power supply.
This is the breakdown of the mass of the system. Most of the mass of the components were obtained from the specification sheets. For the battery, we estimated the mass by looking at the options available online that would fit our requirements. For the mounts, we used the mass properties feature on SolidWorks to find the mass of the mount designs. The total mass is 11,773.5 grams, which is within our requirement of 15,000 grams. Most of the weight is accommodated by the battery. This is the breakdown of the total cost of the project. Our main costs were attributed to the electronic components. Since the system relies on mounts, to carefully secure the components, a significant amount of the budget was allocated to 3D print the mounts. The total cost was $191.08, which was within the estimated budget of $200. There were few limitations when we were designing the system. There was no in-person shop space, therefore we built a prototype of the electrical system with user control and motor and built a detailed CAD model of the drive systems. Calculations were performed to best estimate system performance. Apart from this, testing a real prototype would allow for refinement of the friction drive system. There were no user testing of the system, therefore solicited user feedback through description and design sketches so that we could still incorporate user input. The design requires someone who is physically capable of performing the installation. Therefore, the end user may not be able to do this themselves. Friction drive systems have some limitations in very wet conditions or muddy conditions. The design accommodates 90% of the population, thereby excluding the heaviest 10% of Canadians. We can improve the features of the system by increasing battery capacity and developing a system to optimize power draw. This will allow the user to travel longer distance between charges. We could also improve the packaging of the system to allow for easier installation. Our current requirement is to accommodate the weight of at least 90% of the population. However, in the future, we can redesign the system to at least accommodate 95% by using larger motors and further development of the friction drive system. We could also increase the functionality of the system by adding optimized drive modes for outdoor surfaces and wet conditions.